Okay, we have been looking at samples and populations and comparing the statistic and making an estimation about the parameter for the population. Now, we're going to make a statistical inference about the parameter. So we're going to make a hypothesis, and then we're going to test that hypothesis. So this is called sample hypothesis testing. We're going to start off with some known information about the population, and then we're going to have a claim as to whether this information is true or if it needs to be increased or decreased. We're going to set up that contradictory hypothesis. Then we'll decide how we want to collect data, and we will make a sample, and we'll collect data from the sample, and then we'll determine the right course. So this is the whole, to me, this is the whole purpose behind statistics. You learn how to make a survey and disperse a survey to collect information. Then we learn how to look at that information. Then we can use that information to make estimates about the population based on our statistics. And then now we can say, oh, let's make estimations on our decisions about the whole population, or the parameter on the whole population based on these inferences. Okay, so we have two different hypotheses. We have the null hypothesis, which is the status quo, if you will. It's what's already assumed from this population. Then we'll find an alternative hypothesis. This is what we're claiming, and this is what we're testing. This is going to give us a decision whether we accept the original hypothesis or we do not accept the original hypothesis. I don't know what happened to my screen. Oh, there we go. Okay, so there are three main null hypotheses that you can have. We can say that our mean or our proportion, mu or p, I can say mu is equal to or p is equal to something. My alternative hypothesis in that case would probably be not equal to. Now, my alternative hypothesis, some people call it alternative, some people just call it H1. Doesn't matter, whatever you'd like to call it. Okay, sometimes it's even called the research hypothesis. So we would have mu is equal to or not equal to. If we had, this would mean that we have a two-tailed test. And we'll look into that in a few minutes. I have some pictures for that, and we can see some examples. Okay, now let's say that we have it's equal to, but we want to say, so if we have not equal to, then those are some words you can use. Is we think it's different. We think it is not equal to. It has changed from. It is not the same as. All of these words in the problem will lead you to an equal to and are not equal to. But if you see something like is greater than, or is above, is higher than, it has increased since, it's longer than, then we would have the original is still equal to, but the alternative hypothesis is now greater than whatever parameter that we have. And then the third case, this is a one-tailed test, a right-tailed test. The third case that we can have, again, we can have the mean or the proportion be equal to. But on this side, we would say that it's less than. Same with proportions. I'm just leaving that part off. Sorry about that. So we could say that that our average is actually below the state average, or it's less than, it's decreased in recent years. Anything like that in the problem will lead us to alternative hypothesis of mu is less than. Again, that is going to be a one-tailed test. That's going to be a left-tailed test. And should I show you to show you what I mean by that. Okay, your pages are going to be out of order. So let's say that we have the average is 100 grams, or it's not equal to 100 grams. This is a two-tailed situation. So here's our normal distribution. And what I mean by tailed is that we're going to have our critical value at the left and the right side. Because it's not equal to, then we have to look at both extremes on either side. When we are looking at this information on the normal curve, and we're finding our critical value, z alpha over 2, this is normally called a decision rule. So we can make a decision based on the area that they want us to test, whatever our alpha value is. Usually our significance level, or our alpha, is a 0.05, giving us a 95% test here. I'm going to write that down for you. Significance level is alpha. Well, whenever we're making our decision rule, anything in this 95% area is our do not reject region. So if we find our test statistic inside this region, in between these two critical values, we will not reject the null hypothesis. Do not reject H naught. But this shaded region is the rejection region. If I can find a test statistic within those values, I shouldn't be able to, right? Because this is 95% of the data. Then they are extremely on the outsides of my data. And then we're going to say that, well, this might be a fluke. I'm going to reject my claim and go with the status quo. Okay, so that would be the rejection region. You can find this critical value on your table, like we have been in the last couple of videos, or you can use inverse normal in the calculator. And I'll write you a note for that, inverse norm. And then you just put your information in there. Remember that you're using 0 and 1 for your mean and standard deviation. Okay, now sometimes we have that our H naught is equal to and less than. So we think that the actual amount of, the weight of something is less than 100 grams instead of equal to 100 grams, like the status quo says. Well, this is a left-tailed test. So less than is left-tailed. Notice that it's not less than or equal to. It's strictly less than, because if it was equal to, then it would fall within our status quo. So this time, our critical value is no longer z alpha over 2. It's just z alpha. I'll have the entirety of the significance level below my critical value. So we can say this is the rejection region now, and this should still be the do not reject. Because if I find something above, then it's still not passing my test. I'm only testing below on this case. So this would be z alpha here. This would be the area of alpha down here. Again, this is the rejection region. So if I find something down here, less than, reject alpha. We can reject our null hypothesis. Okay, and then the right-tailed test is the same. The entirety of your area, your alpha, is going to be on this side, leaving you a one-tailed test with z alpha here. Same do not reject the null, but if we find something that's way out here, then we're going to go ahead and reject it and say, whoa, we shouldn't have found this. That means the status quo is wrong. Okay, so let's get back to it. Let's go look at some examples. A statistician read that at least 77% of the population opposes replacing the $1 bill with $1 coin. To see if this claim is valid, they selected a sample of 80 people and found that 55 were opposed to replacing the $1 bill, stating the hypothesis. So we're not asked to do any tests. We just want to know the null and the alternative hypothesis. Now they're trying to trick us. It says sometimes, and I crossed it out for you so you can visually make that change. Sometimes we'll say at least in our null hypothesis. We still write it as H naught equals, H naught is that the, proportion? Because it's a percentage, it's a proportion. H naught is equal to 0.77. That would mean that our alternative hypothesis is, well, what do we think? Well, it doesn't say in this one whether we think it is greater than or different or anything. But the null hypothesis does say at least, so we can assume that we are testing that it is the opposite. So we have the proportion is less than 0.77. YOLO Health Insurance claims that in 2016, the average monthly premium paid for individual health coverage was $283. So that one's pretty straightforward. They're saying that the average, so mu, is $283. Suppose you are suspicious that the average or mean cost is actually higher. So we're going to test that hypothesis by saying mu is greater than 283. And then we could run that test, and it would be a right-tailed test because we want to find numbers that are greater than 283. Okay, don't make this more difficult than it is. It's equal to, and then you decide whether it's less than, greater than, or not equal to from the wording in the problem. Okay. We want to test whether the GPA, the mean GPA of a student in American colleges, is different from 2.0 out of a 4.0. The null and alternative hypothesis are. Okay, now, it doesn't seem like we have enough information, but we have exactly what we need because they said the word different. Okay, so that means our null and our alternative are going to be equal to and not equal to because it says different. And we're talking about mean, so I'm going to use mu is equal to 2 and mu is not equal to 2. I have one more and then we'll get to the different types of errors. In an issue of the U.S. News and World Report, an article on school standards stated that about half the students in France, Germany, and Israel take advanced placement exams and a third pass. The same article stated that 66.6% of U.S. students take advanced placement and 4.4 pass. Test the percentage of U.S. students who take advanced placement exams. Test that it is more than 6.6%. State the null and alternative hypothesis. Okay, so the null is that the proportion of people who pass is 6.6%, which is 0.066. And the the alternative hypothesis, rather, is going to be, we think it is more, so we're going to say the proportion is greater than 0.066. Notice that I changed that percentage into decimal form, so it made more sense to the problem. Okay, now we're going to get into types of errors. There are two types of errors that we are going to talk about when running these tests. So you make a decision rule, and then after you do your test statistic, you have to decide whether you accept or reject these hypotheses that we just created. There are two types of errors that can happen when you start to make this decision. And the best way to look at it is in chart form. So I have a chart here. There's really good charts in your table. Really good charts in your book that do this as well. Some great examples if this is confusing after I'm finished. Okay, so type 1 error is your null hypothesis is true, but we decide to reject it anyways. This is a type 1. So this is true, and we say, oh, no, it's false. But if it's false and we reject it, there's no error. Now, the second type of error is if your null hypothesis is false, but when we do our test, we fail to reject it. And this could be because of any reasons our test wasn't set up correctly, we gathered a sample and it was biased. It could be anything, but it was false, but we failed to reject it is what we care about. That's a type 2 error. So we're going to go through these problems and we're just going to read through what happened and we'll see if we can find the type of error. Suppose the null hypothesis is that Nevaeh's rock climbing equipment is safe. Okay, so we're saying that it's safe. That means the alternative hypothesis would be that it's not safe. Okay, just to keep that in mind. So Nevaeh thinks that her rock climbing equipment may be safe. Okay, so we've decided to accept or not reject, actually. In fact, it's not safe. So we decided not to reject, but it was false. That is a type 2 error. Okay, because she failed to reject it, and it was not safe, right? So that follows this pattern right here. Nevaeh thinks that her rock climbing equipment may not be safe. Okay, so she is rejecting to use it. It is not safe. I don't want to touch it, but there's nothing wrong with it. So that is a type 1 error. Okay, let's get into some more here. Suppose the null hypothesis, H0, is the victim of an automobile accident is alive when they arrive at the emergency room of a hospital. Okay, so the status quo is when a victim of an automobile accident arrives at the hospital, they treat him like he is alive. Label the following either type 1 or type 2 errors. The emergency crew thinks that a victim is dead. In fact, the victim is alive. Okay, so the second part of this is our hypothesis. So the victim is alive. That matches our null hypothesis. The victim is alive. But they treated him like he was dead. So in their mind, they're saying that he was not alive. So that would mean that they rejected the fact that he was alive, right? This is a type 1 error. The emergency crew does not know if the victim is alive when, in fact, the victim is dead. Okay, so the victim is dead. That's our that's the reflection on our null hypothesis, right? So the null hypothesis says that they're alive. He's in fact dead. So the null hypothesis is false. But they don't know that he's not alive. They're treating him as he is alive. So they failed to reject the null hypothesis. This is a type 2 error. Now, different types of error cause different problems. What if type 1 error happened in this case, right? The victim is alive, but they thought he was dead, which means they didn't do the life-saving steps that they would have done, and maybe he could have survived. In the type 2 error here, they might be wasting resources on somebody who is no longer alive, wasting resources, time, and people when they could be using that information or that time and those resources on somebody else. Now, I know that I'm doing this for this victim of an automobile accident, but that's the way the type 2 and 1 errors interact all the time. So if type 1 happens, then so let's look at this other example. So let's say that she was safe and she didn't get to go. Well, she didn't get to experience the rock climbing. She didn't get to go outside. So there's consequences to this error, and there's consequences to this error is what I'm trying to say. Okay. I think that's all the background you need to know. Let's get into the actual tests. Okay, you can do a test for the mean when the standard deviation is known, and we're going to use the normal distribution for that. We're going to assume, or we want our sample size to be greater than 0. I'll talk to you about that in a second. If you don't know the standard deviation of the population, we'll stick with the t-distribution like we learned in the last section. We'll assume that it's approximately normal, so we can assume S is approximately sigma. The sample is approximately the population. We're going to do n-1 degrees of freedom. The sample size on this one doesn't have to be greater than 30 as long as you can assume that it's normally distributed. Okay, and then a test for proportion is the same assumptions that we had to make earlier. We're assuming that it's normally, it's a binomial, oh my goodness, it's a normal binomial, it's a normal binomial distribution, I got this, and that n times p times 2 is greater than or equal to 10. Okay, this is how you find the test statistic. Notice that we've seen these formulas before. If you don't remember them, that's okay. We're going to use them in this chapter. Okay, when running a hypothesis test, there's a couple of steps. Step 1 is to state the hypothesis and identify the claims. Step 2 is to find the critical value from the table. And when we do this, we are going to draw our normal curve and make what's sometimes called a decision rule. So after you find your critical value, you can do that. Then we're going to compute the test statistic, and then we'll make a decision to reject or not reject. Notice that we are not going to accept the null, we are just going to reject it, or we're not going to reject it. And then we'll summarize the results in a conclusion. So in a battery factory, 8% of all batteries are made, are assumed to be defective. Technical trouble with production line, however, has raised concern that percent defective has increased in the past few weeks. Of the 600 batteries chosen at random, 70 of them are found to be defective. Does data support the concern about defective batteries at a significance level of alpha equals 0.05? So just with our first problem, can you see all the applications of this type of math can do for us? So this is just a random battery, and we're checking whether the equipment is running correctly by pulling a sample that they make and testing them and seeing if the equipment is still working as we want it to. Okay, sorry, I'll jump off my high horse. The hypothesis that we want to write down is that we think the proportion of batteries is equal to 0.08 that are defective, which means our alternative hypothesis is P is, we think, okay, there's concerns raised, we think that the percentage has increased, so we're going to say P is greater than 0.08. We can also, okay, so we know some information from this that we're going to need for our test statistic. So we need p hat, but to find p hat, remember p hat is our proportion of our test. So that is of our sample, 70 over 600. So it's 0.117 in our sample. So our sample looks way higher. We can't make a decision based on that. We have to run the test. Okay, so some other things we're going to need is, I think, Q. 1 minus 0.08 is 0.92. I'm looking right here at this equation, so I needed p hat, I needed p naught, I needed q naught, so that I can run my statistic in a few minutes. So I just found all that information and put it up here at the top. Okay. Now, I knew I was doing a proportion because we have a percentage, and I have a number out of a total, so a fraction for my sample. My rule. Now, I printed off some, just a second. My bell curves are not very symmetrical, so I printed some off so I can do this for y'all a lot better than I have been. Okay, so let's look at what this means. We have a one-tailed test because it is a greater than. So we are going to set up, what's the, alpha is 0.05. That is the area under the curve on the right-hand side. So if I fall over here with my test statistic, I will reject the null hypothesis. We just need to know what this number is. So this is 0.08. And we want to find our z. So we can say z equals 0.117. Oops, actually, not yet. Hang on. Actually, we'll save that for our test statistic. We need to know on the normal curve, if that's 0.95, what is the z alpha, or z 0.05. So we're going to check our table. Okay, so I pulled my table out. I'm looking for 95 in the area section. Oh, there it is. 1.6. Well, it's not quite 95, huh? So 1.645. You can do it right in the middle of 0.04 and 0.05. So we're going to say that z alpha is 1.645, which is this number. If we find our test statistic is above this number, so if z is greater than z alpha, then we will reject h naught. That is our decision rule. Now that I've made a decision on where my cutoff is, I can run the test statistic. So we've done this before, where we just take our proportion from our sample, we subtract the proportion that we think it is, so the experimental minus the theoretical, and divide by, some crazy numbers here, the square root of p times q. Excuse me. So we're going to do 0.8 times 0.92, and that's why we found those numbers earlier. And the sample is 600. Okay. Now, again, I'm doing everything by hand. This can all be done in the calculator in different steps, and you can fill that information in your homework, because in ALEKS, everything is just enter your answer, right? So if you're looking for your critical value, this number in your calculator, it's inverse normal, which is like, I think it's menu 653 in the Inspire. You just put inverse normal 0.95. Here, I can write it for you. Inverse norm 0.95, the area, and then don't change the mean and the standard deviation. And it should give you like 1.65. It's the same number. I just have a more accurate number because I use the table. I should have technically checked my assumptions for the test statistic. I forgot. Make sure that N times P times Q is greater than 10. So that would be these numbers, which gives me 44. So my assumption worked. I could run the test statistic. This number is 3.34. Okay, so we found that our test statistic falls like here on our curve. 3.34 is way above 1.645. Now, this tells us, so we can say because 3.34 is greater than 1.645, then we reject H naught. The data does not support the hypothesis of 8% defective. So restating the question again, with my information in it. Okay, let's do another one. An investigator wishes to know whether the proportion of overweight individuals in Indiana differs from the national proportion of 71 or not. So there's our favorite word, differs. It's a big hint into what kind of test we're running. A random sample of 600 individuals results in 450 who are overweight. Test at a alpha equals 0.05 significance level. Okay. So we have a proportion of people again. So H naught is, the proportion is equal to 0.71. And the alternative is going to be that it is not equal to, because we use the word differs. So it's not the same. It could be greater than or less than. We don't know which one. We're just saying that it is not 71%. Okay, so we need our p hat. Our sample is 450 divided by 600, which is approximately 0.75. Ah, okay. This means that Q naught is 1 minus 0.71, which is equal to 0.29, and again we have an alpha of 0.05. Okay. Now, just because we have a 95% significance level does not mean that our critical value is the same. Be careful. This one is a one-tailed test. This one is a two-tailed test. So when you set it up to make your decision rule, it looks a little different. I'm going to first check my assumptions. 600 times 0.71 times 0.29, N times P times Q, and make sure that I can run this test. Okay, so that gives me 123.54, which is greater than 10. So yes, I can run this test. Okay, now I'm going to make a decision rule. So I told you I wasn't going to keep drawing these. Just a second. Okay. So this time we have a two-tailed test where each side here has 0.025, apologies. So it could be really, really high above what we think is average, or really, really below what we think is average here. So we have Z alpha over 2. Now this one you have memorized. I know from doing confidence intervals, if this is 95%, then this is negative 1.96 and this is positive 1.96. So if you memorize those, kudos. If not, you'd have to use the table. And then you remember on this side you're looking for the number that it says, 0.025. But for this tail, you'll have to do 95 plus 0.025. So the whole 97.5. I wonder if I have this right here. 0.02. Hang on, I'll look. Yeah, here it is on the table. 0.975 is 1.96. And then because it's a normal distribution, it's symmetrical. So one is positive 1.96 and one is negative. So what we just found out is that if our critical, or if our statistic Z is less than 1.96, negative 1.96, or if Z is greater than positive 1.96, we will reject H0. Okay, so that's just our decision rule. Now we can run our test to the little chunks here. So our test this time, we're going to have Z equals, what is our proportion? 0.75 minus 0.71, yes, divided by the square root of 0.71 times 0.29 divided by 600. Okay, so that's the difference in ours and theirs divided by the deviation. So that would give us Z equals 2.159. Okay, so now I'm going to go look over here and figure out where 2.159 would land. That's just over 2 standard deviations away from the mean. It's more than 1.96. It falls right here within our rejection region, 2.159. So we reject the H0 because the data does not support the hypothesis that the national proportion, the hypothesis of the national proportion of being 71 individuals. So reject H0. Now the wording on the problem, the answer, this isn't the whole answer again, comes from the problem. The whole answer is the sentence, reject H0, the data does not support the hypothesis. I have a couple of more problems. I think we're going to get into mean. Yeah, here we go. The average hourly wage of the U.S. was assumed to be $10.05 in 1985. Midwest Big Business, however, claims the average hourly wage was larger than this. A random sample of 15 of Midwest workers determines average hourly wage equals 10.83, and the standard deviation of the sample is 3.25. Does data support big business claims at alpha equals 0.05? Okay. Do we know? We do not. Okay, when it comes to the mean problems, you have to check to see if you're given a population standard deviation. If not, then you need to use a t-distribution. If you do, then you can use the z-distribution. Now, everything about the problem is the same except for, of course, the critical value. So you'll have to use different tables for that. Now, if you use the wrong one, it's not the end of the world. Your decimals will be a little bit off. But because they're telling us to assume normality, and they don't give us a population standard deviation, we only have the standard deviation of the sample, we have to use the t-distribution. So I'm just going to write down what we're given here. What else do we have? Oh, our H0 is, the mu is equal to 10.05, and our alternative hypothesis, H1, is that our mu is larger, so greater than 10.05. Okay, we have a sample of 15, which means our degrees of freedom is 14, n minus 1. Okay, now I'm not going to use one of my printed, because remember the tails, the distribution for this one's a little bit different. It's still normally distributed, it's still symmetrical, it's just a little bit taller. So what we're looking for is, what is this tail? We know it's a 0.05% of the data, but what is the critical value? So what is T alpha? Okay, so I grabbed my T distribution table. This again is table, I don't know. But there's an instructions at the bottom if you don't remember how the tails work for you. So if you're looking for one-tailed test, which we are, we're going to look for the one tail to be 0.05. And we're looking for degrees of freedom on the left, and there are 14 degrees of freedom because there are 15 in the sample. And there is our critical value of 1.761. So this T alpha is 1.761. So if T is greater than T alpha, we're going to reject H naught. That's our decision. So if it's greater than 1.761. So the only thing that's left is to run the test by finding the test statistic. So we have our x bar minus the mu over s divided by the square root of n. Okay. So that is 10.83 minus 10.05 divided by 3.25 divided by the square root of 15. And when we calculate that, we get 0.930. Now, that number is closer to the 0 and is less than 1.761. So here is our T. That means, because it's in the non-shaded region, that we do not reject H naught. It fell where we expected it to fall. So if we're thinking of our confidence intervals, it fell in not our 95% confidence interval, right? But a little bit smaller. It fell within the region that we thought it was going to, so we can't say that there's enough information to claim the true mean is above the 10.05. So even though our sample, the average of our sample was above 10.83 or was 10.83, doesn't mean that that is normal for samples. So we cannot reject the H naught. Let's look at a couple more. Yeah, we're almost finished with this. So the program director for an account program is 95% confident that her students scored higher than the average, on the state final. She randomly selected 11 recent graduates and discovered that their mean is 630 with a standard deviation of 23. Assume the underlining distribution is normal. So here we have another one where we're assuming that it's normal. We have a sample size that's pretty small, but because we're assuming that it's normally distributed, we can use the T distribution. So we're going to say that our null hypothesis is equal to, the average is equal to 615. But our alternative is that the average is actually greater than 615. So we have a T distribution and we have a right-tailed test and we're still at a 95. Now we can't use the same number because the degrees of freedom are different. So the sample size is 11, which means our degrees of freedom is 10. So you can use the same number over and over in the Z distribution, but you cannot in the T because they're all different. Okay, so what do we have? We need to know what this number is, right? What is T alpha? On my handy dandy table here, that's the wrong table. On my T distribution table, we still have a one-tailed 0.5 area. So that's my significance level. And we're looking for degrees of freedom at 10. I think we're at 1.812. We're going to compare our data to this number by running the statistic. We're going to take our sample mean, subtract the mean we think it is going to be, divide by the standard deviation divided by the square root of the sample size. Oops. Sample size is only 11, my bad. Okay, when we put this information into our calculator, we get something. Maybe 2.163. So this is way higher than our critical value. So we can reject H naught. There's not enough data to support the state average of 615 on the state final exam. Okay, I'm going to skip this last one. Let me read it real fast. I'm going to skip it because it's more of the same. Please let me know if you need more help. Remember, you know that you need to do the T distribution if there's no sample standard deviation. I mean, there's not population standard deviation. Oh, goodness. Yeah, let me know if you have any questions.